All right. So in previous lecture we talked about recursion and how to loop using recursion. Now, recursion is hard. Like you have the base case, you have a recursive case, and you need to think about tail call optimization. And the recursion is hard. It can be really, really hard to think about. So 90% of the time when we're doing functional programming, we are not recursing explicitly. Instead, we abstract away the recursion so that we don't have to see it. We just let some higher order function take care of it. And that's what we're going to look at in this section. But before we do so, we're just going to have a little brief overview over collection types in F#. These are extremely well documented, so you will get plenty of help from IntelliSense right in Visual Studio Code. There's plenty of documentation on these things on the web, so I'm not actually going to go through all the hoops and loops of these things. I'm just going to go show you that they exist, what they are called, and what their major properties are, and what are the commonalities, and then we'll look at how we can loop over these things. Right. So, collection types. We have already seen the list. So these collection types are all generic types of some generic type arm. They are containers. They take stuff. They provide structure to things. The list is providing structure to things, whatever they might be. And the list has, of course, syntactic sugar in F#, so you can, instead of writing these complicated const nil, we can just write square bracket and element 1 semicolon 2 semicolon 3 and so on. And they also support syntactic sugar for doing slices, so we can say something like 2 ... to 10, which will create a list for you from 2 to 10. And if we have let x equals like this, there's also an indexing shorthand instead of using the list.at method and so on, which is x dot and then a square bracket and then an index like 2. Again, careful with these things, because they might throw an exception. Because if you're trying to access an element which isn't there, so this is actually a partial function, and we need to be careful with those. Then there are safe variants of these where there's a try something, and then you will either get an option type to back. So then you get either some value or none if that element isn't available. So a little bit depending on if you're doing life support equipment, then you most certainly want to use those versions and not this. Or if you use this, please check that you are within bounds yourself. Otherwise, you're going to have a nasty surprise one day. So this is a list. One of the features of this list is it's a linked list, which means that it's super cheap to add stuff to the head of it. So it's really a great sort of little thing where you can push stuff on and you can pop things off. And there's a shorthand operator for that, which is the function which we've already seen once, I think, colon, which you can pattern match on, and you can do all these things. But you can actually say something like this, 5, and then you have 1, 2. And this would produce the list 5, 1, 2. Note that this always goes to the head of the list. And if you are a C programmer or a C# programmer, you probably would like to think of putting stuff at the end of the list. But a lot of the times it's not really necessary to put stuff at the end, as long as you know where you put it. Because I've seen people work with lists where they, I need to append something to the list, so they start by reversing the list, then doing append to the head and then re-reversing it just to add one element, and then they do this 1,000 times, and that's horribly inefficient and completely pointless. Like, if you know that you get your list in a certain order, then you know that you have it in a certain order and just deal with it. Just as a little warning. Right, so here we have this list concatenation operator, which is super convenient. So the list is really, it's like this lovely invention. But if you need to pick out elements in the middle of the list, and or go to the end of the list and do things, or append to the end or to the middle of a list, then it's a very inefficient data structure. And in general, also for like really doing high performance work, the list is not what you want to use. But a lot of the times we're dealing with small lists with some tens of elements, and then it's usually a very good choice. It's very convenient to work with, and we get all the benefits. So this is really like the bread and butter of a lot of the stuff that we do. But we need to be aware of that it has its limitations, and there are cases where we definitely do not want to use the list. Another little remark that we have, which is important. This is a fantastic choice. I was very irritated by the fact that why did they choose the semicolon to be a list delimiter? There's a good reason for it, because this is an alias for a new line. Like this is an explicit sort of new line thing. So this list can actually be written like this. 1, 2, 3. Get rid of this here. List end. No semicolon anywhere. So you just put a new line instead. And this we will see later on in this course, will turn out to allow us to write some really beautiful code. We can do some really nice stuff by using this. Because sometimes we don't have simple elements here, we have some complicated stuff, and we can have function calls, and we can have all kinds of things inside this list, and we just new line, and oh, we get this. We can get. You'll see. I'll keep it as a surprise. So that's basically the list. So if you need a more performant array of elements, one-dimensional, two-dimensional, three-dimensional, then there is the array. And that's a fixed size thing. There are also variants of it with resizable array and so on, which have extra methods on them so that you can resize them and so on. But in principle, this is a fixed size thing. You will create it to a certain size, and then you will manipulate it. But still immutable though. There are also immutable versions and so on. But so typically what you would do is you would have some data source, and then you will say array from list or from sequence or from some iterable source, and in the background .NET will do it efficiently, will make sure that it builds this array object, immutable array object, by probably using some mutable stuff in the background, but it's well tested and well analyzed so that it's okay. We can just trust it. Arrays have similar syntax to lists. We have a shorthand, which is bracket pipe, and we can say 1, 2, 3 pipe square bracket. But since this is a fixed size thing, now we have efficient random access to it, so we can index it in the same way with a .index thing and so on. This is very efficient because it's just pointer arithmetic. You don't have to traverse anything, you just go and pick out the element. But we don't have any sort of easy appends a single element to a list. What you do is you have to append a array to array. And these are expensive operations, because probably you have to reallocate everything and to create these things. So again, for certain things lists are good, for other things arrays are the absolute clear choice for doing things. And there's a much more, the API for arrays is much more limited than for lists. So in general, make the consideration, is this going to be something which demands a lot of performance, or is it just a small little thing where it's more important that you have a good programming interface? Go for lists. I always go for lists first. Unless I know it's going to be 1,000, 2,000, 5,000, 10,000 elements in it, or 100,000 or a million, then there's no point in going for the list, because then you know that it's not going to be very good. Unless you are basically building it and consuming it in sort of from end to end, then it might be fine. All right. And lists are of course very good when you don't really know beforehand how much data you're going to get. So that was the array. Then we of course have something which is map, which is a dictionary parameterized over two types, key and value. And these are the key is hashed, so you get the tree structure where you can just look up the key very quickly. This is just normal dictionary, like in Python and in C# and whatever. And you can create these like so let m equals map of list, and then we can give pairs. So now we can say foo, comma 1 bar, comma 2, and so on. So you can give it a list of pairs, key value pairs, and it will create the map for you. And there are plenty of other methods on it. You can check if the map is empty, you can check whether an element exists, you can just try to pick out elements from it, risking an exception, and so on. So there's a rich API for these things, and you can, there's a lot of stuff in there. And easy to combine maps and so on. And then of course we have the set, which is similar, but just parameterized over one value. And sets are binary trees of unique elements. So all of these will it computes the hash and stores it in a tree based on the hash, and then you can do very quick lookups of elements in a set. But you can only have exactly one of the same type, which is of course a very good feature, because if you are putting in 10 times the same thing, you will just have one copy. So that's a feature one can use sets to get rid of duplicates when building stuff. And of course all of these things can be turned from, so you can make a set from, do a set of list or of array, and there's of seek and so on, and you can also convert them back to lists. So back and forth. So these things are isomorphic in the sense that you can put stuff into this form or out, and you don't lose any information. So these are the most important ones, and then there's a whole bunch of generalized versions and mutable versions and so on. The ones I've shown you here are all immutable. You define them, and you can add to them. There's like, you can say map add or set add or so on, but what you will get back is a new set. And of course by now we know that since we can trust that the original set is not going to change, adding an element to it isn't a particularly expensive operation. But you also have mutable versions of these which actually mutate the actual object, if someone needs that for some weird reason. So all of these things here, if you go and look in .NET, they have something in common. They all implement a interface, object-oriented interface, which is called INF-3910-5. Yes? Which means simply iLoopable. or I traversable, or I whatever you want to call it. It means that every element has an order in some kind of order in some way, and you can enumerate them and ask for them, which means that you can index them. And if we know from typically from object-oriented programming is that this is a sort of a, well, this is an interface now, but you could think of it as a super class to these things. So you could cast everything upcast it to an IEnumerable and then just use that property of the thing. And you have something slightly similar, which is a thing called seek, which is a generalized container which you can loop over, and which we will see how to do in a little second. So seek is sort of the generalization of list, array, map, set, and a whole bunch of other things. And all of these things can be turned into seeks. So you can, if you have some function that you need to just transform some data, you can, instead of writing it as that it takes a list or an array, you can say this function takes a seek of and now you can use it with arrays and maps and sets and lists and whatnot, trees of all sorts. Very, very nice thing. But it comes at a penalty, because this will do iteration in a particular way, which is not necessarily the most efficient way for all these data structures. So if you are in a region where performance is paramount, probably you don't want to put it to a seek. But in a lot of places, it's a really nice way of making code, avoiding code duplication and making things general, is using seek. Which is this just says this is a sequence of some kind, which again builds on this. One of the things with seek is that it actually turns all of these things into lazy data structures. What that means is that it will not treat your data structure as a each element. So we can sort of think of this list of things. 1, 2, 3. This is not how seek views the world. It sees this thing as a function of an index I, which returns a value and a new function of an index I to the next element. Right? Which means that every time you access an element, it will call a function to produce the value of that element, and again, in principle, a new function to the next element, to the next element, to the next element. So this is the laziness of it, which means that you can actually do things like, you can say seek.infinity, and then you give it the function fun I to produce elements for you. And now you've just produced an infinite list, because you can just keep on pulling elements of this seek forever and forever and forever and forever until your computer dies. So this is something to be aware of, and this is a super useful property. In fact, the language like Haskell, everything is lazy by default, which is kind of cool, and also kind of hard in certain situations. It becomes difficult to sort of really fully understand what's going on. Things will happen at will. So that's seek. And it has methods like seek empty to create an empty sequence, and it has seek singleton to create a sequence of single element. And we'll see later when we talk about monoids why this is useful. And you can turn any list into a seek, and you can turn any array and map and all of it. You can turn them into seeks. There are all these nice properties on it. So just exploring in Visual Studio. Now, to get the looping, because now I've been rambling on about these collection types. And the whole point is just to get to the looping bit. So recursion is hard. So what we tend to do in functional programming is that we tend to abstract away looping and put it into something that will do a particular kind of looping over some kind of structure. This is very abstract now. Let me explain. And you've seen these functions already, but now we can look at them in a slightly new light. So for example, if we take list, we can say list.map. And now we've seen map a couple of times already. Map is a function which takes a function as its first argument, a to b. As this is list.map, it takes a list and produces a b list. Right? So map is a function which will take a function and it takes a list of stuff. And this A is that A there, right? So what map will do is we'll take this container and it will transform it through this transformation function to produce a new container of a new type. And this is a cool thing, because if I read some code and it says for I in some container do, I really have to read the code very carefully in the loop what it's doing, because from the first line there I don't know anything about what it's going to do. Nothing. It might take a list or a map and produce a integer, or it might be calling databases, or it might do, I have no idea, really. I need to really read the code to see what it's doing. If I see map, I immediately know what's going to happen. I know that it takes a data structure and it returns an identical data structure. It doesn't change the structure of the thing at all. So if I give it a list of 5 elements, it will produce a list of 5 elements, but with its contents transformed. So one way of looking at this is like this. So if I say list map f on a list of 1, 2, 3, this produces a new list which is f1, f2, f3. And the same goes for array. And the nice thing is that if I'm looping over a map or a set, it doesn't matter. If I loop over a map, I will get the two. I can either loop over keys or values or both. So I can have a function which takes 2 arguments, one for the key and the value, and but it will produce an identical data structure for me. And I already know that when I read map, I know that, okay, this is not going to change the structure of the problem, it's just going to transform the data. And this is important. Makes for readable code once you get used to it. A wonderful abstraction, where we abstract all the effects of stuff into this F, what we want to do, and then we'll just let somebody else care about how to recurse over a finger tree or a rose tree or something else, which you would sit and scratch your head and be completely desperate for hours to figure out how to recurse over those things. Somebody else's problem. We've outsourced it to the F# gods at Microsoft. Right, so that was map. Of course, map has a twin, which is, I'm just going to use list, but this applies to all of these container things. I'm going to list.filter p and a list. So we're going to see what these things are, but the signature of filter is it takes a function, a to bool, a list to a list. It looks like I'm going to have to change my pen again. I'm running out of juice. So the reason I call this P is that we call it a predicate. It's a function which takes an element of some kind and produces either true or false. And this means that I can, if I have something like 1, 2, and 3 in my list, and my filter here says, I could just say that this function here is less than 2, partially applied less than operator applied to 2, then it would be true for this guy, false, false, and the whole result of this would be just a single element of a single list. And this is nice because I know when I see filter, I know that it will return this a data structure of the same type. It cannot change the type, but possibly with fewer elements in it. Might even be the empty list. So it allows us to throw out stuff from things. Hence filter. Right? And then the last guy that we're going to look at, and this one this one is the most powerful one, and also the most complicated one. And that's when map and filter don't do in combination. Then we need to do something else. And now I'm going to look at the fold. And I'm actually not going to go through all the details and theory of fold. You can look it up. There's quite a lot of stuff to be said about folds in general. There's plenty of nice theory about this, but it's fairly easy to use once you get the hang of it. And the fold is a general. It's basically it's just a way of saying a sort of simple recursion, where you know that you can just get element after element, and it's somebody else's problem to provide you with the element. So this is like, if I know I have something that can give me something which is I-enumerable, something which gives me elements, then I can fold over it. And the fold takes a function of 2 arguments. So we'll have, I will write this like this now, just to be quite explicit. Fun a x something, and it will take. So in the case of a list, I will just give it an empty list to start with, and some list of elements, 1 to 10. So let's see what this fold does. So this function here, the first argument to the function is something we call the accumulator. We've seen it already when we did the tail recursion. And this is the current value. So when the fold starts, it will take this initial value here. This is the first value. It's only used in the first iteration. So it will take this initial value and pass it into here. Then it will take the first value of the list and pass it into here. And this function here will do whatever it wants to do, and it will return a well, now I should probably not have used an empty list here. I'm just going to call this I. This might be whatever. We're not restricted to lists. So what it will do here is it will receive this I as its initial element, and then it will produce a new value which will get fed into A for the next iteration, and then it will pick the second element from the list. So this is keeping sort of updating stuff. And of course, if I want to do a sum, we already looked at how to do a sum. I could do this with a list.fold, and I can say fun a x, and then I can say x plus a. This here will become my new a. I'm just going to call it A prime, which will in the next iteration go in here. And then I say 0, that's my initial value, I'm going to feed it in and I can say 1 through 10. And this thing will sum all the values from 1 to 10. But I could do something else. I could say, well, the initial value is an empty list. I could say it could be a map or a set or whatever, really. But if this is a set, if this is an empty list, I need to make sure that this is a list. So what I could do is I could say, well, okay, I could do say A plus X, append it to A. Oh, not A, sorry. I could do, yeah, okay. X plus 1, whatever, something. Add 1 to every element in the list. Since this is now producing a list, this was a list, this needs to be a list. So you're free to do pretty much whatever you want with these folds. They're powerful. But the problem with the fold compared to map and filter is that when you see fold, you really need to read this function very carefully in order to know what it's doing. Because it might take a long list and squish it into a number. It might take it and expand it into a list into a two-dimensional list. It might take it and convert it into contacts. Who knows? Whatever. We really don't know what's going to happen until we have read this very carefully. So it's the most general one, but also the least transparent one. I should mention that this particular fold that we're using here is a case of a so-called left fold. And this has to do with how we recurse, whether we are sort of right or left associative in how we compute things. Do we do things as we go along, or do we go to the end and then fold it up? Basically, these are the two options that we have. And this is the left fold. There is a variant of it which is called fold back, which is going to the end, and so this is just building up things as we go, whereas the fold back will go do nothing essentially as it goes to the end of the list and then do everything on the return. And whether you should use one or the other depends. Depends on if you are building something which has a particular order, you need to pick the right one. List.fold back. There's a little idiosyncrasy with fold and fold back, because when I give this function here, I need to give xa. So you see in the fold we get the accumulator first and the variable that we are current value second. In fold back it's reversed. And there's a thing, this is also called a right fold. So this is the left fold and this is the right fold. And if you want to expand your brains, you can go and read about right folds, because right folds are so-called primitive recursive. Which means that this can generate any recursion. This one can't. But you can actually implement this fold in terms of that fold, but not the other way around. And if you want to do something that's gonna hurt your head, yeah, it's a good exercise. It's good fun, but it hurts a bit. So that was looping. Now we're done with that. Now we got that out of the way. In the next lecture, we're going to look at mutable state and exceptions. Then we only have a little bit of object-oriented stuff and a little bit of odd bits here and there, and then we can sort of, we basically have a wrap on F-sharp, the language, and we can start looking at the really good stuff. All right, until later.